So this talk will be basically on fiber-reinforced rare earth-based bulk superconductors. So I work with bulk superconductivity group with John, David, and others in the group. So very shortly, I think we should go to the next slide. Hold on. Okay. Yeah. So here are some of the people in the group. So when I joined the group, some of them were here. Mark was out on a holiday probably, or he was in Australia. So he's not there. So his photo is here. I guess you can see his photo. And others who have joined the group a bit later. Dominic, apologies, I couldn't put your photo in, but others are all here. Okay, so I'm just working out the mouse configuration. Okay. Okay, so today's talk is basically on rare earth-based bulk superconductors. So I'll be focusing on yttrium-based bulk superconductors whose critical temperature is above 77 Kelvin. So roughly between 90 and 95 Kelvin is the critical temperature that we are going to concentrate on for this talk. But there are also other superconductors, so there is no introduction required for this group. So we fairly work with liquid nitrogen very well. So among the high temperature superconductors, you can see yttrium-based superconductors or rare earth-based superconductors have good irreversibility fields. So very high irreversibility fields, and as a function of reduced temperature, the performance of BCO is much better than the other high temperature superconductors. In this context, this is a brighter candidate for practical applications. But we'll come to that in shortly. There are a few hiccups that we need to basically address, and I'll try to address some of them. So there are different forms of high temperature superconductors that people are working on, but in the bulk superconductivity group, we are basically working on bulk material. So this is a single grain grown in the bulk superconductivity group. So Hua grew it, and this is about 40 millimeter in diameter. And this is a single grain which can trap about 1 Tesla magnetic field at 77 Kelvin. So this is an extraordinary trapped field at liquid nitrogen temperature. There are also other configurations that I worked on at the University of Liège. I had experience, I gained experience on thick film configurations. So they are basically used for shielding applications. And coated conductors, we did little work with the Culture Institute of Technology. So we tried to do in the economical version, not the PLD version, but the solution deposition work. So this was with KIT Cambridge. There was a collaboration program under which we did a small amount of work. So I gained experience in all different domains. So single grains are essential for these bulks to see the light of the day. So if you don't put a seed crystal and if you don't make a single grain, then you end up with multi-grains, which means within the grain, though the current carrying capacity is very high, but across the grain boundaries, the current carrying capacity is very, very low, which means you cannot basically transport the current from one end to the other end, which means you also cannot get large magnetic, you cannot trap large magnetic fields. So also you can see with misorientation angles, the current carrying capacity dies down. So these are with different misorientation angles. You can see the current carrying ability is basically down. There are a few processing techniques like hot seeding, which was basically coined initially, and later the cold seeding, which was developed, and this is completely the technique now being followed to produce rare earth-based bulk superconductors, both in research laboratories and also in the industries like CAN and ATZ and others. They are all producing single grains following this approach. So not only yttrium, there are many other rare earth elements which can be used, and the periodic temperatures are slightly different. Depending on what rare earth element you use, the periodic temperature is slightly different. So there is a lot of processing that goes in order to transform this material into a single grain. Only once you make this into a single grain, the currents the macroscopic currents can be supported, and that basically enables you to have a conical large magnetic trap field. So these are the A growth sectors that you see on the top surface. And this is the cross section where you can see the growth facet lines here, and this is a C growth sector. So you have this sort of crystallographic geometry, and as made it is in tetragonal form, and you need to oxygenate it in order to make it orthorhombic. Though the single grain performance is very good, but making these single grains is a big challenge. Hua and others have put in a lot of effort within the bulk superconductivity group in order to develop this strategy, and later on we all joined the group and took this processing technique further forward. A buffer pellet technique was introduced because very often with the single grain, if you have to make, the seed crystal has to be intact in order to ensure that the heterogeneous nucleation and single grain growth can be promoted very well. If the processing conditions fail, then you basically end up with either partial melting of the seed crystal or complete melting of the seed crystal, and this will be catastrophic. So you won't be able to get single grains. But if you use a carefully designed buffer pellet strategy, then the reliability with which the single grains can be made is much, much better. So we have done a detailed work to see what buffer pellet composition is made and how it can be basically used to transform in order to produce large single grains more reliably. And also the advantage with using buffer pellet is the seed crystal is basically neodymium, which means the lattice mismatch effects are all absorbed within the buffer pellet, which means your sample is very clean and free from these artificial defects, which means your sample has fewer cracks and pores, which is an added advantage with the buffer strategy. So we can make much bigger single grains now with a very small seed crystal, because very small seed crystals, they are easy to be fabricated with perfect orientation. So we can use smaller seed crystals and use similar time scales in order to grow such a big sample. In 2014, gadolinium-based bulk superconductors were used, and we got a trapped field of 17.6 Tesla, which is the Guinness record till now. That's the highest trapped field in bulk superconductors. Okay, we also have a slightly different strategy, which is called infiltration and growth technique, using which we, in a simple YBCO system, we could get 14.3 Tesla, and this is very reproducible. So this is yet another processing technique that we have been working on for the last 4-5 years very intensively. Even earlier, we had both these processing techniques, but we have optimized several configurations in infiltration and growth and melt growth. And finally, we have come to a stage where the success rate is very high. You can see not only yttrium, there are many other systems now we can reliably make within the bulk superconductivity group, and the success rate is definitely above 85%, which is, I think, extraordinary. We can even grow bigger samples. I think Hua is now working on an Excel project where she's trying to make even bigger samples, like 80 millimeters and 100 millimeters. So it's a big challenge, and we are working on it very intensively. Okay, so having said about the single grain fabrication, but still there are a few problems that need to be addressed. Firstly, the main problem is you have very weak mechanical properties, because these are single grain ceramic samples. So when they are exposed to large magnetic field, the Lorentz forces are so high that the cracks can be generated within the single grain, which means you can see here the trapped field profiles of 2 samples which were brought back after NHFML measurements at Florida. And you can see they were exposed to 18 Tesla magnetic field, but they got either a partial crack or a complete crack, which means you get 2 lobes here. So it's not a single grain anymore, but there is a small amount of trapped field here, 0.39 Tesla at 77K, because these samples were brought back from Florida, and they were measured in the bulk superconductivity group at liquid nitrogen temperature. So when the field of about 1.4 Tesla was applied, it only trapped about 0.3 or 0.39 Tesla. So this tells us that the mechanical properties have to be addressed. The superconducting properties, I think, more or less have been saturated after a thorough optimization studies. But now the point that has to be addressed is the mechanical property, and that is what we looked into for the last 2 to 3 years. Okay, So there is something called a Brazilian test where you apply load onto the sample in such a way that you keep applying the load until a crack like this appears. So this is the center. So this is the seed crystal location, and these are the growth sectors. And you can see a crack appearing right across the sample. So we do this in order to see physically through Brazilian test what is the maximum stress, tensile stress these samples can basically take. And once we had an idea about this, we thought of reinforcing these samples with fibers. So during this journey, initially Kaisen, a PhD student, started off this work. We were working on fibers, basically, different varieties of fibers like tungsten, silicon carbide, and many fibers, basically, titanium. All these fibers we basically investigated to see if they are reinforced properly, though it's a big challenge because the single growth itself is very complex. Once you introduce elements like tungsten or titanium, which have melting points higher than the peritectic temperature of the YBCO or REPCO itself, then the chances of getting a single grain is very minimal. So when we started off this work, when Kaisen proposed this, I think David and I guess even John probably said, "Oh, good luck." So it's a very big, complex problem that had to be addressed. But when Kaisen started off, I was also there. I just joined the group, so we both started off this work, and then Wayne joined us as a visitor, and he also was very interested with this work. Then a lot of discussions went on, and we had initial amount of data. So I'll quickly show you about the tungsten and titanium fibers. But essentially, silicon carbide was chosen as a potential candidate. So before going to silicon carbide, I'll quickly show you about tungsten fiber. You can see before making a sample, so with the precursor powder, tungsten fibers were added, and we have done DTA studies to see if there is any shift in peritectic temperature, and there was not much shift at all. It was like plus or minus 2 degrees centigrade. That was within the error bar of DTA itself, so we didn't change our heat treatment schedules a lot for this, but we could grow single grain. So you can see these fibers protruding out. So these are all tungsten fibers that were made. We tried to increase the size, and you can see the fibers protruding out because we had a lot of fiber initially. Though the trapped field didn't change much, but it means that the superconducting properties were not enhanced, but probably the mechanical properties enhanced. But when we looked at the critical current density measurements, it was slightly better. So we did a detailed SEM analysis to see what was the reason, and we found that there was a 2411 phase. So tungsten got into 2411. So Y2, BA4, and CU1 and W1. So this is the elemental ratio that we found, and it's a 2411 nanophase basically. These square-shaped ones were found to be 2411. So it is good in terms of JC, but from the mechanical properties, it really didn't help. You can see the standard YBCO was sitting here about 19 megapascal. 8 into 19 is roughly the tensile stress of a standard YBCO. But with tungsten fibers, because of these fibers protruding out and creating additional cracks, the tensile stress basically dropped to about 15.6 megapascal. So for every batch, we tried at least 3 to 5 samples. And what I'm showing you is sort of an average. So after that, we went to silicon carbide fibers. And even here, we did similar DTA studies to see if there is any shift in peritectic temperature. Not much, but a very little change. But this was taken care in the heat treatment schedules. And we could grow single grains using these silicon carbide fibers. The trapped field was a single conical profile. And you can see that compared to the tungsten fibers, silicon carbide fibers were better, but still not the best that we wanted to have. But it is still within the similar scale as a standard YBCO. Then we came up with, this is just to show you different configurations we tried. Like we dispersed these fibers in the powder, then we arranged them in different configurations. and all of them worked because thanks to the buffer strategy. So all this helped in order to grow single grains, even when silicon carbide fibers, which have higher melting temperatures, were still there in the matrix. So you can see the trapped field performance is sort of similar. So reproducible results are there, and then we went to hybrid fibers. So what you see here is a hybrid fiber, which is essentially what I should show you here. So this is a hybrid fiber. So you have a tungsten core here and a silicon carbide matrix here. So you have basically a hybrid fiber which is helping, and it is also very fine. So which means the probabilities that it protrudes out is minimized. So you can see very thin fibers. These are about 100 micron. Yeah, 100 micron. So we reliably, the single grains could be fabricated because we have paid attention to the peritectic temperature changes, if any. Trapped fields were much better than the tungsten and silicon carbide fiber added samples, and the trapped field performance was very similar for 20 millimeter diameter samples. This is a good trapped field. Then we measured mechanical properties. So Brazilian test was used, and we found that about using just a little fiber, we could get about 40% improvement in the mechanical strength. The tensile strength has increased by 40%. So this was very, very interesting. Then very recently we also, okay, before telling you about that, let me show you in this SEM micrograph, you can see a good adherence of the fiber. So the fiber has not worn out. So the tungsten is still sitting here. We have done some EDX to find out how much the tungsten has moved out or silicon carbide has deformed. But the results were very encouraging. So we had a very good intact fiber sitting in. We also tried with this with the infiltration growth work. Even there, the results were promising. And here I show you with three different fibers. So this is the tungsten fiber. All were initially circular, but you can see they all smeared out, whereas the hybrid fibers retained their shapes. So they were intact, and this is the core sitting here. This is the tungsten. So we did some EDX to find out if it was tungsten, and it is tungsten. So which means the fiber could sit intact within the matrix without disturbing the single grain growth. So that was a promising signature forward. We patented this technology. So this patent is under review. So both UK and international patents are there. Very recently, we were trying to investigate the potential of fiber-reinforced samples. I haven't put those slides yet because we are yet to finalize it amongst ourselves. But what we have understood is when you reinforce these single grains with fibers, the cracking mechanism is very different. So if a sample without fibers cracks, then all the field basically vanishes. So when we have a 12 Tesla magnet into which we put these samples, the fiber reinforced samples and standard samples, and we compare the performance. The standard samples, once they break completely. So all the field is vanished. So like 0.3 Tesla or 0.2 Tesla is what is remained. Whereas when you have these fibers, then if you had trapped like 14 Tesla or even whatever the field that we applied, I think we applied something like 6 Tesla, but after cracking, it still had like 4 Tesla. So which was good. So which means the crack didn't propagate all the way to the edge of the sample. So the fiber probably stopped it. So we used these fibers at different levels of the sample. So I think the fiber, wherever it was there, it probably stopped the crack. So we are doing even detailed analysis to see the cracking mechanism and trying to understand what is really going on in these fiber reinforced samples. But as of now, the fiber reinforcement is definitely helping from mechanical property point of view, and it is not it has not deteriorated the superconducting property, which is an added advantage. So I think we are planning to investigate it slightly further, but due to COVID, everything has come down. and I have a strange situation, so we could not accelerate to the point what we really wanted. But to whatever it is, to sum up, the results are really promising. So the fiber reinforced samples, if they can show at least this performance or even higher performance, then I think all the superconductors probably around the world, where you need to put them in challenging applications like flywheels and others, wherever bulk superconductors have to be used, whether in motors or whatever it is, where you have subjected to large magnetic fields or to mechanical stresses. I think this is probably the way forward to use the reinforced samples so that the mechanical properties are at least addressed to a larger extent, and the failure probably is reduced. So I think I'll stop at this, and I'm happy to take any questions.